Okay, well, I hope everybody is doing all right today. We're going to continue with probability. I'm hoping that we are able to get to this supplementary material today. We should be able to. But Thursday is going to be when everything is due. If you have any outstanding assignments you want to turn in or retakes, say of the previous exam, or if you wanted to correct an assignment, all of that's going to be due by Thursday morning at 8:05, and we'll just go ahead and continue moving on with probability. It'll most likely take us in the next week, considering last year students found a little bit difficult when we started talking about conditional probability, but I'll see if I can help you out this year. Other than that, any IB junior who's going to be taking a test this year, don't forget you have that registration fee of $172 due by the 15th. You can talk to Mrs. Moore. I believe you can pay it out if you need to. They just you need to get everything settled by the 15th, or at least get everything going. Does anybody have any questions? Okay, then let's get back to it. We were talking about probability, which is the desired outcome over the total number of outcomes that we were talking about. And we had several axioms we were going to look at. Our probability was always going to be between 0 and 1, again, 1 representing the 100%. Mutually exclusive means that there's no intersection, there's no overlap between my events. So they cannot occur at the same time. Now, if they're mutually exclusive, then the union of the two events is just going to be the probability of the first plus the probability of the second. If they are not mutually exclusive, that means there is an intersection. Then in order to find the probability of the union, we have to subtract off the intersection. And that's actually what this one little packet is going to help us with today. See that a little more clear. And I think we talked about a tree diagram. And then we also created a lattice diagram. Okay. All right. So let us see what problem we are on now. There you go. You saw what I did there. Okay. I think we made it to this one, right? Now, this one is not in your notes, but I did want to go ahead and talk about it. I found it off a resource. I think it's a really good problem. So this is another version of a lattice diagram. Okay, and it says use a two-dimensional grid, which we have here, to illustrate the sample space for tossing a coin and rolling a die simultaneously. Okay, from this grid, determine the probability of tossing a head, then getting a tail and a 5, or getting a tail or a 5. Okay, so take about 1 minute. Try this on your own. Write down on a piece of paper, your notes somewhere, what you believe this would be. If you want to go ahead and jot down this, you can. If not, you can just follow along. It is going to be on the video. Okay. But you'll notice I've created this diagram using the vertical. That's either heads or tails for flipping the coin, or rolling the die. You've got 6 faces on that. We've got all the different combinations you can get. So we first want to know the probability of tossing a head, probability of a tail and a 5, and getting a tail or a 5. So those key words that we were looking at with respect to the sets, those are again going to play a big part. Okay, so let me give you a little bit of time on that. Does anybody think they already have all 3? Okay, 1. Okay, so I'll give you a little more time. Okay, so let's start thinking kind of big picture. How many outcomes are possible? Yeah, 12. You can see that easily from the diagram. You can flip a head and then get any of the one side of the die. Tail and the same thing. So I want to know what's the probability of tossing a head. Now you'll notice it doesn't say anything about what? Okay, the die. So I'm just wanting to know what's the probability of getting a head. It would have to be 1 out of 2. Okay, 1 out of 2. Okay, because no matter what I roll on the die, that doesn't matter. There's 6 possible ways to get ahead along with the faces of the die that I'm going to roll. So the 6 out of 12, it's got to be a 1/2 probability. Even if you just ignore the die altogether, you still only have 1 out of 2 outcomes for the coin. Does that make sense? Okay. Well, let's try this next one here. Getting a tail and a 5. So what's that key word that I was just referring to? And. Remember, that's the intersection. Okay. So what would you guys think? Does anybody think they know it? By show of hands? Okay. Libby, what do you think? 1/12. That's exactly right. There's only one possible way to go ahead and get a tail and a 5. Okay. Any other version is not going to result in that. So 1 out of 12. Good. Good, good. All right. And our last one here, getting a tail or a 5. Well, what does that or mean?
Union.
That's the union. Okay, so getting a tail or a 5. What do you guys think? That would be 7 out of 12. Yes. Very good. Is everybody okay with those? How many people had all 3 of those right? Okay. So for the people whose hands are not going up, is there anything I can do to help? Okay. One thing I really hope is that, these coin problems, they do make sense. Makes sense.
We'll just have to roll the dice.
Okay. To coin a phrase. Okay. All right. So let's go ahead and work a few more of these problems. Now we're back on your notes. All right. It says a letter is chosen at random from the letters of the word together. Okay. Find the probability of selecting a T. All right. Well, let's go ahead and start with this. How many possibilities or outcomes are in my universe? Yeah, because there's 8 letters in the word together. Now, even though some of them repeat, okay, those are still possible outcomes, right? So there's 8 total. And I'm looking for the probability of selecting a T. Well, how many of those would we call favorable outcomes? Yeah, there's 2 T's, right? So the probability would be 2 out of the 8 total. So I'd say there's a 1 in 4 probability of getting a T if I just randomly chose. Okay. Find the probability of selecting a consonant. Okay. Well, how many consonants do I have? Okay. 5? Okay. I'd agree with that because we have 3 vowels. Okay. So 2. Okay. The probability would be 5 out of 8. Okay. And that's not going to reduce, so we don't have to worry about that. Find the probability of not selecting an E. Okay. Now remember, we talked about this yesterday. If I compare this to sets. Oh, hello. Okay, Evelyn and Sierra. Did yours say when convenient as well?
This is now.
Okay. This one says when convenient. There we go. All right. And is it over there, sir? That is the practice. Here, let me go ahead. Let's see. We look in Monday. So here you go, sir. Here are the notes. And the other one's that focus activity I already gave you. Okay. All right. Okay. And then 3. Oh, what were we talking about? What is this if I relate it back to sets?
E prime.
Okay, E prime. So we're talking about the complement, right? So I'm looking for anything but an E. So how many letters would that be? 6. So for 3 here, the probability of not selecting an E, okay, well that would be 6 out of 8. So that's going to be 3 out of 4. Oh, did someone knock again? We're popular today. Oh, hello. Oh, there you go. Okay, any questions on together, this problem? Easy? All right, well, let's try this one. A coin is tossed 3 times. Draw a tree diagram, and from it, write down the sample space. Use the results of part A to determine, or to obtain the probability of obtaining 1 tail, at least 2 tails, 2 tails in succession, or just 2 tails. All right, so let's start with the tree diagram. Take about 30 seconds. We're going to flip a coin 3 times. Okay, what you're doing is trying to show visually all the different possible outcomes of flipping a coin 3 times. So let's just start with the tree diagram, and then we'll go back to the probability. All right, so I hope this problem doesn't stump anybody. I'm on fire today. Oh, goodness. Okay. Okay, is everybody about ready? Or do we need a few more seconds? Okay. Well, let me go ahead and create the first flip. So if you flip the coin, there's only two possible outcomes. So either I'm going to get a heads or I'm going to get a tails. This would represent the first flip. Then from each of these, if I get a heads, well, then I have another possibility on the second flip of either getting a heads again or a tails. Same thing for the tails. Okay, this would be the second toss. And then I'm going to go ahead and do this one more time. There's two possible outcomes for each of these four that I now have. So this would be heads, tails. This would be heads, tails, heads, tails, heads, tails. Right. Okay. This is what everybody came up with? So if I flip a coin 3 times, there are 8 possible outcomes. Okay, so we first want to go ahead and find the probability of obtaining only one tail. So if I'm looking through, how many outcomes is that going to happen of the 8? Okay, so 3 out of the 8? Okay. So do you guys want me to go through and highlight these as I do so, or like I did yesterday? Sure. Okay. So let me go ahead. I'll just do it in red. Okay. So the second branch is definitely going to give me just one tail. What are the other ones? Okay, we have the third, right? And then what? And then we have tails, heads, heads. So the fifth. Okay. So that is absolutely right. Okay, so for one here, the probability would be 3 out of the 8 total outcomes, so 3/8. Let's try the second one. I find the probability of obtaining at least 2 tails. So is it okay if I get more than 2? Yes. Okay. What am I looking at here? Okay. So again, you're saying it's 3 out of 8?
Oh, I know it's 4 out of 8.
Okay. 4 out of 8. Which one did he miss? I believe he said heads, tails, 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 heads, tails. Okay. Then we also have tails, tails, heads, and tails, tails, tails. So there is 4 branches that satisfy this. Okay. All right. So the probability is 1 out of 2. So basically a 50% chance of that occurring. All right. 3. What does it mean 2 tails in succession? There you go. So one tail has to follow the other. It doesn't necessarily have to be the first 2 or the last 2 as long as you have 2 tails in succession. So if I'm looking at this tree diagram here, the first time I see that happening is going to be in this 4th branch. Would you guys agree? Where else does that happen? Well, it definitely happens for tails, 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 and tails, tails, heads. So it looks to me like I'm getting 3 outcomes. Okay. So 3 out of the 8. Good. Okay, so the probability would once again be 3 out of 8. Okay. And now finally, what's the probability of obtaining 2 tails? So remember, this is different from the other one. So this one time, the tails, tails, tails cannot be a part of this. We only want 2 tails. So it looks like I have 1, 2, looks like I'm finding 3 outcomes. Okay. All right, so the probability would once again be 3/8. There we go. Okay, any questions? Anybody having difficulty? Okay. I believe, good. This is our last problem, and then we should be able to get over to this guy right here. So we're given the probability of A occurring is 0.6, the probability of B occurring is 0.3, and the probability of A intersecting B is 0.2. So we want to go ahead and find the rest of these. So let's go ahead and start with this. The fact that we're told there's an intersection between these two events, would they be mutually exclusive or not mutually exclusive? Not mutually exclusive. Okay. Not mutually, I'll just go ahead and put EXCL, exclusive. Because over here is the dead area where it doesn't like me to write. Okay, so I want to go back to the first part of the notes very quickly, and I want to focus on one part of this. Okay, this part right here, if A and B are both sets of U and they are not mutually exclusive, that means they do have an intersection, then the union of the probability is to add the two individual probabilities and subtract the intersection. Okay. Now, I not only want to go ahead and show you this using the formula, but I also want to help you visualize this on a not unit circle. That's pre-calculus. A Venn diagram. Excuse me. I kind of started thinking about previous ones. So let's go back over here. So what was the probability of A? Okay. So the probability of A plus the probability of B minus the probability of the intersection. Okay. So the probability of A was 0.6 plus the probability of B? 0.3, and now I'm going to subtract the probability of the intersection because they are not mutually exclusive, 0.2. So what should I be getting? 0.7. So the probability of the union should be 70%, right? Okay, so let's go ahead and visualize this in a Venn diagram. Let me get... Okay, let's see. Oh, those just fit perfectly. Yes.
So are there parts of the group other than A and B? So like
There could be, yes.
like the elements like
Because the rectangle, the universe, has to be 100%.
okay, so since
So there could be a percentage of neither of those events occurring.
A and B union is 0.7 and then the intersection of A and B being 0.2, so there's like a 1% chance that you grab something that just wasn't either.
Yes.
Okay.
Okay.
And sorry, is the A intersection, is that like a different fitting element?
Well, it's one of the, we haven't really gotten to that part yet. We're going to kind of elaborate on that more when we get to conditional probability. But like, you remember the problem we were just doing with the tree diagram? What we're going to come to find out is that, like with tree diagrams, if you have these individual probabilities, like for example, if we're actually looking at the numbers, the probability of throwing a head is just 1/2, right? And for this type of problem, each of these individual probabilities would be the same, right? Well, what we're going to find is that if you go along the branches, like what's the probability of throwing all 3 heads? Well, that would be 1/2 times 1/2 times 1/2. Well, that would be 1 out of 8, right? You're going to come to find that, oh, that didn't happen. Where's my highlighter? You're going to find that the branches themselves represent the intersections. And then if I want to take the sum of the ends of those different branches, those represent the unions. Okay, so we are getting there. We're just not there yet. Okay, but you see how, like here, that probability is exactly what the Venn diagram is visualizing. There's only the one way out of the 8 to get the 3 heads. Okay. All right, so yes, that is coming. All right, so let's go ahead and see with the Venn diagram if I do get the exact same answer. We know that the intersection of the 2 has to be 0.2. All right, so what would be here just for A? Okay, 0.6?
No.
Now remember, A is 0.6, but 0.2 is part of that.
So it'd be 0.4.
So it'd be 0.4. Remember, because the whole of circle A should be 0.6, right? Okay. Ooh. I'm feeling kind of silly today. Sorry. I don't know. It's a Tuesday. I'm really excited about tomorrow. It's Halloween. I get to dress up like the Joker. And it's like I get to be me the one day of the year. Anyway. Okay. Anyways, what should I put for strictly B? There you go, because B, the full circle should be 0.3, and we've already got 0.2, so this is 0.1. So think about it. Remember, how have we described the union before?
It's their elements combined.
Yeah, it's just the marriage, the way we described it, right? Everything together. Well, take a look. 0.4 plus 0.2 plus 0.1, there's your 0.7. Okay. Now, also, think about this, and Eli was bringing this up just a second ago. These two sets together only represent 70%. What am I missing?
The universe.
Yeah, in the universe, there has to be 100%. So somewhere out in the rectangle, but not in the sets, I'm missing an additional 30%. Does that make sense? Okay. So why don't we go ahead and try this? I want you to try B, and I want you to go ahead and try C. All right. Take a little bit of time. Now, whether you want to use the formulas from the front, or if you want to go ahead and focus on the Venn diagram, either or. Let's see what you guys can come up with. Is everybody ready? Okay. Now, if you're going by, say, for example, the formula, the probability of, what do we call that little prime again? Remember, that's the complement. Everything in the universe but outside of that particular set. This would equal the probability of the universe, so 1, everything happening, minus what? The probability of B. Okay. Well, if we think about it, 1 minus the probability of B occurring is 0.3, so it looks like we should be ending up with what? 0.7. Now, we should also be able to get the exact same answer if we're just looking at the Venn diagram. So if I want everything in the universe outside of B, well, you'll notice if I go ahead and shade everything outside of B, the only thing I'm adding up is the 0.4 plus the 0.3, which again gives me the 0.7. Okay, good. Good, good. Let me go ahead and take those off there. And does anybody think they know what the answer to C is? The intersection of A and B's complement. Okay, Emily, what do you think? Okay, she's got 0.4. What do you guys think? I would absolutely agree. The only intersection between the two is going to be this crescent section right here. Okay. To find that, by the formula, you go ahead and take the probability of A minus the probability of the intersection of A and B. Okay. Good, good, good. How many people got that right? All right. Is anybody having trouble? Anybody having difficulty? Okay. Well, before we move on to that little supplement packet I gave you today, again, let's go ahead and take a look at these axioms 3 and 4, specifically the formulas here. If two subsets of a universe, okay, basically two sets, if they are mutually exclusive, that means they have no intersection, well, the probability of the union is just the sum of the individual probabilities. Okay. If they are not mutually exclusive, that means if they do have an intersection, you still add the two individual probabilities, but you're going to subtract the intersection. Okay. So let's go ahead and take a look at this. That is the homework you will eventually be getting. Here we go. Okay, so mutually exclusive and non-mutually exclusive events. So let's say here are my two sets. Let's say we've got set A, which contains the outcomes 1 and 3, and then set B, which is only going to contain the outcomes 2 and 4. So you have a die. Event A is the truth set of rolling a 1 or 3. Event B is the truth set of rolling a 2 or a 4. Okay, so what's the probability of event A occurring? Yeah, see, we have two possibilities out of how many total? 6. Okay, so that means we have a probability of 1/3, right? Would you guys agree? Okay. Well, let's go ahead and take a look at the probability of B. Well, wouldn't it be the same? Yeah, because we got two possibilities out of the 6, so that would be a 1/3. Okay. Well, let's go ahead and now take a look at this. Let's take a look at the union. Okay. The probability of A or B occurring. So if I were to roll a die, I'm thinking about the probability of getting either a 1, 3, 2, or a 4. That'd be 4 out of 6, right? 4 out of 6, which is 2/3. Now, go ahead and take a look at the individual probabilities that we just came up with. If I take the 1/3, the probability for A, plus the 1/3 probability for B, it will give me the 2/3 probability for the union. See, it should match up. This is only going to work if these two groups are disjoint. Remember, that means they have no intersection. Or as we're now calling them here, they're mutually exclusive. So one set's just going to have, the 1 and the 3. The other one will have the 2 and the 4. Is everybody okay with that? Okay. Well, let's take a look at this. Let's say we have, again, two events. Let me go ahead and finish drawing this circle around here. Everything always comes full circle. There you go. They do get around. Anyways, event A is the truth set for rolling a 2, 4, or 6. All right. Event B is the truth set for rolling a 4, 5, or 6. So this situation has an overlap. So these two sets, they are what? They are not mutually exclusive. They do have an intersection. In fact, what appears in both? Okay, 4 and 6. All right, so let's say this is A, this is B. So 2 appears in A and 5 appears in B, right? So let's go ahead and take a look at their individual probabilities. What's the probability of rolling a die and getting either a 2, 4, or 6? 1/2, because we have 3 outcomes over 6 total. So that's 1/2. Okay. Well, let's do the same thing for probability B. Again, 4, 5, or 6. 3 out of 6 total, so it's 1/2. Okay. So let's go ahead and compare it to what we did just a moment ago. If I go ahead and add these two right now, 1/2 plus 1/2 is going to give me 1 or 100%. Why is this not possible?
Because you're forgetting about the 1.
And yeah, you're saying that there's a 100% chance that any of these 4 could happen. But yeah, we're not even including the fact that we don't even have all the possible outcomes here. Does that make sense? So in order to make this work, and that's what this is talking about right here, if we know that they're not mutually exclusive, in fact that there is an intersection, once we add them, in order to get the union, we have to go ahead and subtract off what the intersection is. So how many elements were in the intersection? 2. So 2 out of 6, that would be 1/3. And let me go ahead and revert back to what we had. I'm going to go back to the 6s. So this would be 3/6 plus 3/6 minus 2/6. Okay. So how many 6s would that give me? 4 6s, which would be 2/3. Okay. Now think about it. If we were to go ahead and take the union of the two sets, okay, A union B, yeah, it would just be 2, 4, 5, 6, right? So see, we've only got 4 outcomes that we want out of the 6, which would still reduce to the 2/3. Okay. So what I'm trying to show you here is just kind of give you an example as to why the formulas are written the way they are. Okay, so it's really important to know whether the groups have an intersection, they're not mutually exclusive, or they don't have an intersection. They are mutually exclusive. Okay, what do you guys think so far? Okay. Probability is exciting, isn't it? So exciting. Okay. Independent and dependent events. Okay, so let's say I have some pieces from a Scrabble game. Two pieces have an A on them. Two pieces have an E on them. I put all four in a bag and randomly choose one of the tiles. I would have a 50% chance of getting an A, and the same for E. That makes sense because for an A, there's two A's out of the four. Same for the E's. Now, we're going to go ahead and create the tree diagram in just a second. But the probability changes if I decide to go ahead and do something or not. All right. Choice one. I'm going to place a piece back in the bag replacement. The probabilities are not going to change. Okay, so let's go ahead and create the tree diagram along with this first choice. Then after I go ahead and choose one, I'm going to put it right back in the bag. All right, so now let's go back to our tree diagram. So on the first draw, I have either an A or an E, right? Now, what's the individual probabilities of that happening? Okay. So to pull out an A would be 1 out of 2. To pull out an E would be 1 out of 2, because 2 out of 4. But now, for this first choice, let's say I do go ahead and pull out an A. I'm going to put that A right back. So to continue this, for the second choice, what's the probability now of pulling out an A? It's still 1/2 because I put that tile back in. Same thing for the E. 1/2. And then if I had chosen an E first, well, it's going to branch off in the exact same way. All right. If I go ahead and draw an E, but then put it back, I've still got a 1 out of 2 chance of drawing the A or a 1 out of 2 chance of drawing the E. Okay. Now, what do you think we're going to refer to this as? Would this be independent or dependent? Okay. What's that? Independent. Because, see, the new probability is in no way affected by what previously happened. Okay, it's independent because I'm placing it back in there. Now, what would have happened had I decided to keep that out? Then it would become dependent on the previous probability. Does that make sense? You guys okay with that? That's the difference here between independent and dependent. Okay, so what we just said, they're independent. The probability of the second event has in no way any dependence at all on what previously happened. Okay. Now, let's go ahead and finish this up right here. It says, what's the probability of getting 2 A's in a row? Take a branch and follow it through. So you remember I was talking about this with Eli just a second ago. If we look at the individual branches, what are those when it relates back to sets? Starts with an I. Remember, those were intersections. If I start combining different outcomes for what I want, those are the unions. So like it said, go ahead and follow the branch that has both A's. Okay. Well, what I'm going to do is, as I go along, I'm just going to multiply the individual probabilities. Okay. So if I were to go ahead and choose A twice, but I put the A back every time I did, what's the probability of getting 2 A's? 1/4, 25%. Okay. Is everybody okay with that? All righty. And then let's see what this one says here. Choice 2. You're going to start out with the same 4 pieces in the bag, 2 A's and 2 E's. Okay, you're randomly going to pick them out. But let's say this time I don't replace the letter that I picked without replacement. Okay, so let's go ahead and create my Venn diagram, my tree diagram here. So A and E. So now we're going to start off with the same. If I have 2 A's and 2 E's, well, what's the probability of first drawing an A? 1/2, 2 out of 4. The same for E. Okay. But see now, because I am not placing that one tile back into the bag, this new probability is now dependent on that, the fact that I didn't put it back. All right. So what would be the probability of choosing another A? There you go. Because if I take one tile out, there's only 3 remaining, but only one of them's an A. Okay. So that would be 1 out of 3. What about the E? That would be 2/3. Because at this point here, say we've pulled an A, but I had not yet pulled an E yet. So there's still two E's in the back. And does anybody notice anything as you're looking along the branches? You should be getting a particular sum.
1.
Yeah. Okay. 1/2 plus 1/2, that gives you your 100%. Okay. One of the ways you're going to know that you're getting these probabilities correct is that you should be able to add those and get that 1. In fact, here on this one, what's the 1/3 plus 2/3? There's your 1. There's your 100%. Okay. Now, it's going to switch when we get down here. Let's say that we pulled an E first. To pull a second E, well, that would only be 1 out of 3. See, at this point, we haven't pulled out an A yet, so there are still 2 A's out of the 3. So again, the 1/3 plus the 2/3 is going to give me the 100%. Okay. So now, if I want to know, say, the probability of getting 2 A's in a row, okay, well, I'm just going to follow that branch. So if I were not to put the tile back in after having drawn it, what's the probability of pulling 2 A's in a row? 1/6, 1 out of 6. So again, kind of to emphasize what we were talking about yesterday, if I were to perform this little experiment 6 times, at least 1 out of the 6, I should be pulling the 2 A's. How we doing? Okay, no questions? That's good. All right, then I'll tell you what. Let's look at this one. I really like this problem. What I want you to do is go ahead, go home tonight. I haven't given you the homework assignment yet. See if you can set up this problem. Okay. If you're able to come to a solution, great. If the only thing you're able to do is come up with the tree diagram, perfect. Okay, but at least try to come back tomorrow with something written out. So it says there are 3 boxes on a table. The first box contains 3 white balls and 2 black balls. The second box contains 1 white ball and 1 black. The third box contains 2 white balls and 2 black balls. Without looking, you take 1 ball from the first box, put it in the second. You then take 1 ball from the second box, put it into the third. Finally, you choose 1 ball from the third box. You just move right along without looking. Okay? Here's the question. What's the probability that the last ball you choose is white? Okay. And then counter to that, what's the probability that the last ball you choose is black? Okay. So I'll tell you, the way I solve this one here, it sounds more confusing than it really is. If you create a tree diagram to represent these 3 choices, it makes it so much easier. Okay. All right, so I'm going to go ahead and let you start looking at that. And if somebody wants to come on up tomorrow and show me what they got, or just even tell me the probability, it is super quiet in here. Okay, I'm going to go ahead and stop there. All right, thank you guys so much. You did a great job, as always.